I'm Davide, real pleasure to be here. I'm going to talk about FiDe, which is our latest work done with a group of amazing co-authors from all over Europe. So, there is a large number of highly available core services which run 24/7 in a distributed manner in cloud data centers. And these include distributed databases, distributed key value stores, but also modern use cases such as resilient large language model training, as we saw in the previous presentation, disaggregated memory, high frequency trading, a whole lot of applications. And a common factor of these services is that they often use a failure detector as a building block, which encapsulates both the detection and the notification of failures to the above layers, making sure to ensure liveness and also fault tolerance of these applications. Failure detectors commonly use a heartbeat system to detect the inactivity of an application. So we have applications which send periodic heartbeats to the failure detector. And if the failure detector does not receive the heartbeat for a given amount of time, it times out and then it notifies a failure. And here we have the heartbeat problem. So how do we set this timeout? Timeouts must account for jitter in both processing and communication in a given interaction in between these two modules. So the issue is, how do we choose this timeout? And this timeout can be easily set to large so that the failure detector can really make sure how to that the failure that the lack of a heartbeat it observes is indeed a failure and not just a delay. On the other hand, we can choose our timeout to be too small in order to detect failures timely, but these failures can be falsely suspected as it might be just a delay. Multi-level or gray failure detectors are a state-of-the-art approach to tackle this issue. So their strategy is to install a network of spies in every layer of a given system. These spies are custom code which can be made to detect any type of failure, which it includes crashes, but also deadlocks and other kind of malfunctions which fall under the umbrella term of gray failure detector. So by being close to the monitored application, these spies can quickly detect a failure and issue a failure notification to the failure detector. However, even these methods suffer from the long-standing problem of the timeout. So what happens when a spy crashes? Then the spy that was monitoring that spy still have to resort to timeout. And these timeouts are again subject to jitter, communication and processing jitter, and still go back to the timeout large versus small timeout trade-off, in which we need to give up either timeliness or reliability. Our system proposes a different approach. We focus on crash failure detection first, and we strive to build system-driven synchronous interaction among the processes of our failure detector, which we call FiDe. Basically, these synchronous interactions ensure that messages, which can be failure notification or heartbeat, are delivered in a synchronous fashion, so in a bounded latency. And by doing so, we can use reliable timeouts. Furthermore, our approach is also non-intrusive, using iOS watchdog by monitoring the failures from an operating system point of view, which we'll outline in a second. FiDe can be integrated with the existing failure detector, offering its feature to the gray failure detector, and also achieving the best of both worlds by increasing coverage of gray failure detectors. So we can summarize FiDe contributions into two. The first is what I just explained, which is achieving reliable and fast crash failure detection through the establishment of synchronous interactions. And the second one, arguably even most important, is to build to use FiDe to build simple and efficient coordination in even beyond the failure case, so in failure-free execution. So we'll focus on the first one for now. So the first objective is to build reliable and timely detection and processing. So we can think of a system as split into two different domains, as you can see in the diagram. The best effort domain is the usual environment where applications run as scheduled by the operating system using resources in a best effort manner. What we enforce instead is the FiDe domain, where we use resource reservation, power management system, and resource isolation to make sure that FiDe processes run uninterruptedly. Then, to monitor a crash in phase one, we use what we call the OS watchdog, which basically consists in we instrument the kernel with a K-probe to immediately detect once a process falls out of the operating system table, which is our definition of a crash. Then this notification is broadcasted through FiDe reliable layer to remote processes, which intercept the notification through eBPF XTP hooks, which intercept the packet as soon as possible in the network stack, therefore bypassing the usual jitter introduced by traditional network stack. Then our system focuses on the network. So we also want reliable processing, but also reliable communication in the network. And we achieve so by enforcing a custom traffic engineering protocol and using IP multicast in order to achieve bounded latency in the network. So basically, our traffic engineering system uses high priority queue, reserves high priority queue for FiDe traffic, and establishes multicast trees among FiDe processes. So basically, when a new process wants to join, it needs to ask the FiDe controller first. It's represented by the green interaction in the diagram. And the FiDe controller will assign this process some resources, namely the rate at which this process can send heartbeats and the size of these heartbeats, as in Ethernet size packets. This ensures that overlapping trees will never exceed the high priority queue's capabilities, ensuring the bounded latency. Then we use redundancy to cope with network failures. So network failures can occur in a tree, but we establish two redundant trees among FiDe processes so that we can easily overcome a failure. And then once that failure occurs, the FiDe controller will initialize a network recovery process, which consists in building an alternative tree instead of, for instance, the purple one that we see here, to re-establish the two-level redundancy. There is, however, a case in which that FiDe does not tolerate, and we call this critical compound failure. So if we have a very quick succession of two network failures which exactly hit the two redundant trees, then we're done. However, we estimate the probability of this of being one every roughly 23 years based on real-world measurements of a popular study, and we believe this exceeds this consists in a very reasonable uptime for a lot of services. This graph shows our results, in which basically FiDe achieves both synchronous interaction and a very low failure detection timeout. So on the y-axis, you see the maximum observed latency, and on the x-axis, you see the number of packets that we measure in our system. Our test was run for several weeks and collected more than 200 billion packets. So you can see how the blue line, which represents FiDe, is very flat, meaning that FiDe quickly reaches the worst case latency and then maintains that latency throughout the entirety of the test. While other approaches, including fast network data paths such as RDMA, do not keep continuing showing outliers, meaning that they suffer from congestion and/or contention in the end hosts. Therefore, we can use this 45 microsecond with a small safety margin as worst-case timeout, showcasing how our approach can reach reliable timeouts at the microsecond level scale. We'll now move on to the second contribution of FiDe, which is using it as a building block for simple and efficient coordination algorithms in failure-free executions. To this end, we devised two novel consensus algorithms. The first one is called heartbeat stabilizing uniform consensus, and I'll only go briefly about it in this presentation for the interest of time. The main difference of our consensus algorithm versus classical consensus algorithms such as Paxos and Raft is that it doesn't require a majority of processes. But basically, the reliability of FiDe ensures reliable leader election, hence we can count on acknowledgements from all the processes, hence tolerating more failure than traditional asynchronous protocols. Our second algorithm, heartbeat uniform consensus, exploits a characteristic of FiDe, which is basically the piggyback mechanism. So application can use FiDe to piggyback their messages in order to expose the reliable layer, and which is reliable delivery and timely delivery, up to the application layer. And these mechanisms allows applications to count on even stronger guarantees, further improving the complexity of the algorithms with respect to the previous version. So, in essence, there are two takeaways here. First, FiDe improves protocol simplicity, and that's why we could design two for a paper. Because strong reliability guarantees allow for a stronger model which greatly simplifies the conception and design of these protocols. Then, the other takeaway is that FiDe can improve performance of these protocols even in the failure-free case. So it goes beyond simple crash detection and can be used as a building block for novel services which are simpler. We showcased it in our final test, in which we implement HSUC and HUC into Redis, the Redis key value store and Zookeeper, and compare against those systems using classic state machine replication services alternatives, namely Raft for Redis and Zab for Zookeeper. So in the plot at the top, you can see the set request throughput, in which, for example, taking the purple line, we can see how Redis FiDe with the hack version outperforms Redis Raft by roughly 1.5%, thanks to its algorithmic advantages. The same happens with Zookeeper, and we have specular results for latency. So we achieve roughly half the latency in all our tests. In conclusion, our work shows that we can implement robust timeouts by enforcing data center selective synchrony, which means reliable interaction only in a subset of the data center. And we do so by using kernel support for stable processing, network reservation, and traffic engineering for the network and communication layer. This allows FiDe to achieve microsecond scale detection, and this reliability, FiDe's reliability, importantly enables simpler and more efficient protocols, even in failure-free executions. For the future, we hope to work with modern hardware offload systems, such as SmartNICs, which seem very suited for this selective synchrony model, and this is our current focus. Thank you very much, and I'm happy to take any questions.